Welcome to ISD 609, week 14. So we're using the one of the Professor Chennick's online book, Practical Optimization, A Gentle Introduction. This is a link of the textbook, and we're going to use chapter 12 of the textbook, Integer and Discrete Programming via Branch and Bound, to explain the integer programming, because integer programming is also a very important subset of the math programming discipline. So assuming earlier we studied that studied linear program, in the case that we have to constrain that x1 and x2 not only larger or equal to 0, i.e. non-negative constraints, they are also integer. So meaning that the feasible region changed now. It's no longer the whole region, it's only those discrete points, right? So if the objective function for this particular case is no longer somewhere here on the boundary, it could be, this would be the integer optimum. If you run, this is a LP optimum, but you could not round up or round down to find the integer optimum. That's why we need this new technique on integer program. So branch and bound is one of the methods for solving integer and discrete programming problems. So essentially meaning that for each variable it could be 0, could be 1. For the second variable it could be 0, it could be 1. And this is a full enumeration tree. But in reality, we don't really need to enumerate all the possibilities. That's the reason we're going to go over some of the techniques that we can use to improve the process of solving these types of problems. So there are some important branch and bound terms. Node, right? So here, example of the node, and leaf, but bounding functions, branching, growing, expanding a node, and review this, and depth first, breadth first, and also termination rule. So branch and bound address meaning of a node in the branch and bound tree. How can we select the node? What variable we should select first? And some of the important of the concept fathoming and proving. So for example here, this is an example, a minimization assignment problem. In here we see that the minimum is actually happening at D. So in this case, we don't really need to go over the rest of the branch at the moment. We could just start thinking about going, if we start task 2 on D, what's going to happen, right? So here, if we continue with this branch, we have to, we need to go over this very carefully later in the class. And this is the just an example here, a continuation of the example. And traveling salesman problems. And this is the best route. Okay, the success. Have a good bounding function, get a good incumbent early, find ways to identify nodes, and try to find sub-optimizing very large problems. So this is a homework for this chapter. Thank you.